Deal today of cross-spectra, three-corner hat, and Groslambert covariance. In my latest seminar, I introduced what was the Bayesian approach in order to measure uncertainties and variance, and I will try to illustrate that with other problems. And the problem I will illustrate is first is Groslambert covariance, and second is cross-spectra. It's in reverse order. Okay, and you remember that my last seminar will be devoted to holdover and long-time extrapolation. Sorry. Okay. So today I will give you a brief reminder of what I presented not last week, the latest seminar, and I will present after that an example with of application of the Bayesian estimation with three-corner hat and Groslambert covariance, which are quite the same. I will describe a little bit that. It's not my only job, it was the job of Eric Lantz and Enrico Rubiola. And I will finish by another example, which is an example with cross-spectra. And this is mainly the job that did my PhD student, Antoine Baudiquet, that perhaps you know. Okay, so let's go to what I said in the latest seminar. You remember that we have two worlds. There is a model world in which we have the algorithm. An algorithm in the model world, what you have is a pure number, which is a so-called parameter. I will call it theta, but it can be the invariance, it can be something else. But it's known by using a mathematical expectation. Mathematical expectation, it means that it's an infinite average, so it's not directly accessible. What is accessible in the measure world is what I call the estimator, or the estimate, which is here, or the measurement. And the measurement is obtained with a finite average. So this finite average is an image of the mathematical expectation, but it can be considered that if you are in the model world, it's basically a random variable. But if you are in the measure world, in our world, you know what was the measurement. This one is known, but you don't know what is the parameter, and you have to know it because it's the parameters that we are searching for. But since we want to get a confidence interval around this parameter, we will consider it as a random variable, even if in the model world it's a pure number. Okay, so we want to try to estimate what is this quantity, knowing the measurement xi, which is here. Okay. So it's so-called the direct problem if you know the parameter and you deduce from the parameter the measurement. But the measure world, it's the inverse problem. From the measurement, you have to deduce what is the parameter and make a confidence interval around it. So you remember that I presented the Bayesian inference. The question is how to go from the inverse problem from the direct problem to the inverse problem. In other words, how is it possible to know the PDF? The PDF is the probability density function of the parameter estimate, knowing the measurement. And you will try to assess it from the probability density function of the measurement, knowing the model parameter, which is generally well known. You know if it's Gaussian, it's chi-square distributed, and so on. So in this, for this purpose, you will apply the Bayes theorem, which is this one, and you see that you have here the probability of the measurement knowing the parameter, which is generally known, and here you have the probability of the parameter knowing the measurement. And this is really what you have to do. And in order to do that, you have to define what is the probability density function of the parameter without any measurement, before any measurement. We will see that just after that. And this one is generally not necessary because what we know is this is a probability density function, so it means that its integral from 0 to infinity is equal to 1. It's normalized, so we don't care of this quantity. But what is very important is the fact that you have you need a probability density function of the parameter before any measurement, and this is the so-called prior, and it's denoted generally pi of theta. And generally, it's you determine the coefficient which correspond to the probability of the measurement by normalizing this integral that, as I just said previously. So, what is a prior? The prior should be not informative, because if you make more information in the prior than in the measurement, it's a problem. So, what happens if you don't know anything about the parameter theta before the measurement? You don't know anything, not even its order of magnitude. I show you during the latest seminar that you should consider a prior which is proportional to 1 over theta. What happens here? I don't know. So if you have a prior which is proportional to 1 over theta, it means that it will give exactly the same probability, whatever the order of magnitude. Here is the example from 10 to the minus 18 to 10 to the minus 17, and here an example from 10 to the plus 33 to plus 23 to plus 24. You see that you retrieve exactly the same probability. So it's really what we need. So it doesn't depend on the order of magnitude, so it's a suitable prior, and I will use it just later on. There exist also more sophisticated priors, but we don't care today. Okay, so let's go now to the three-corner hat and the Groslambert covariance. What are the differences between these two terms? First of all, the question is, how is it possible to estimate the stability of one clock? Generally, what we do, if you have a clock, which is not a very good clock, this one, for instance, you need a reference which is much better. For instance, you have a cesium clock here, and you consider, and in this case I think it's perfectly true, that the instabilities of the reference are completely negligible regarding the instability of the clocks. So you will estimate directly the instability of the clock, quite sure. But what happens if you have a good clock? I mean a clock which has the stability which is the same order of magnitude of the reference one. So in this case, you cannot neglect the instabilities of the reference. So in this case, generally we use two clocks which are approximately similar. We have with the same instabilities, and you consider that in this case, the instability you get are 2 times the stability of each clock. But what happens if these clocks are not really the same, if they are not similar? How is it possible to retrieve the stability of each clock? And in this case, you can use a set of 3 or more. You can use 4, 5, 7, what you want, clocks, a clock A, clock B, and clock C, and you measure clock A versus clock B versus clock C, and clock C versus clock A. And from all that, it's generally possible to retrieve the stability of each clock. It's a so-called three-corner hat. Here is my three-corner hat. Each corner is a clock A, clock B, a clock C, and between each clock there is a time interval counter. Between A and B I have a time interval counter that I called AB, of course, and this one will give you a measurement. It's YAB, it's designate, let's say, a frequency deviation measurement, but you can also retrieve the measurement YBC between clock B and clock C, and YCA between clock C and clock A. An important thing is the fact that we have an assumption which is done. You assume that the clocks are totally uncorrelated. Sometimes it's not true, but it's very difficult to go further, because if there are correlations, you will not see them, so it will be an error. For instance, if you are all your clocks are in the same room and you know that they depend a little bit on the temperature, and the temperature change, you will have a change on all clocks, and it will not be possible to detect it because you will see all the clocks varying at the same time. And the second assumption which is done is the fact that you make all the measurements between B, C, C, and A and B at the same time, synchronously. If you do that, you can write the frequency YAB, which is here, which is the difference between the frequency deviation of the clock B minus the frequency deviation of the clock A, plus the measurement introduced by the time interval counter that I call here YM, M for measurement, AB of K. Because, yes, I didn't say that, but the parameter K here, the index K, sorry, counts for time. At each time TK, you have such a measurement. So you can do that for every time interval counter. We will introduce a new quantity which is Z. The advantage of using this, Z is nothing but the difference of two adjacent samples at time tk and time tk plus tau. And if you do that, and if you divide by square root of 2, you will write the Allen variance very quickly, because the Allen variance will be directly the mathematical expectation of this squared quantity. Here you have this complete formula with the 1/2, which is given by the 1/over square root of 2. Okay, so it's only to reduce the equation and in order to simplify what I will write later on. So remember that Z is the difference of two adjacent frequency deviation samples. Okay, there is also, but I will go back to that, a closer relationship, because we can demonstrate that if you had all the measurement between CA, BC, and AB, you will obtain something which is equal to 0 if there is no noise, but if there is noise, you will obtain directly a measurement of the noise 3 times, because we can assume that the variance of the noise of all the time interval counters is the same. It's another assumption. Yes, reminder, my symbol here means mathematical expectation all along my talk. So, what is the three-corner hat method? Remember that ZAB is ZB minus ZA plus ZMAB, which stands for the noise of the oscillator, the interval counter. So if you calculate the variance sigma square AB, you have the mathematical expectation of this. So you can say that it's a mathematical expectation of ZB minus plus the mathematical expectation of ZA, a mathematical expectation of the square of ZB, sorry. And the mathematical of the square of ZA, it's the reason why there is no longer a minus sign here, plus the mathematical expectation of the square of the noise of the counter. So you have the variance of B, the Allen variance of A, and the Allen variance of the noise of the counter. We can do that, yes, the assumption, we consider that the noise of all time interval counters are uncorrelated and has the same variance. We have the same noise level for each time interval counter, which is somewhat logical. So we can build this system. For instance, for the time interval counter, it's the sum of B plus the sum of the variance of A plus the sum of plus the variance of the noise, and it's true for every variance of for each time interval counter. But if you add the first two lines and you subtract the last one, you see that you will remove. For instance, if you add this to 1, you will obtain 2 sigma square B, and you will have sigma square A and sigma square C, but you will, if you subtract this one, you will remove sigma square A and sigma square C. So you will retrieve only sigma square B, and if you divide by 2, you will divide also the noise by 2. So it's the first approach, which was given by Gray and Allen in 1974. Allen from is the Allen of the variance of, the advantage is that you get the stability of clock B, but you have also the noise which is here. The other approach, which, yes, very important, the fact that these are mathematical expectations, but with a finite average, you have an estimate. You see that there is a hat. At each time there is a hat, it's a finite estimate, a finite average. It can be negative, because sometimes if the noise of the clock B is very low regarding the clock A, the uncertainty of the clock A can hide what is the noise B. The other approach was given by Groslambert first and Olivier and Gagnepin in 1981, and it was called we have called it Groslambert covariance a few years ago in tribute to Jacques Groslambert, who was engineer in our lab. And the idea is to see that we have a variance here. Allen variance is a variance, but it exists also the covariance. So if you replace the square, which is here, ZAB, by a product of ZAB multiplied, for instance, by ZBC, what we obtain is directly a covariance. It's a covariance of AB versus BC. And if you develop that, you will obtain this mathematical expectation. So you will, if I develop, I will obtain all the cross terms which are there. But since all these terms are uncorrelated, all these terms will vanish. So we will retrieve only what remains. It's the square of the variance of ZB square. So this is exactly what we call the Allen variance of B. So there is a minus sign, so you have the result of the covariance is directly the variance of B with a minus sign, but it's a detail. But it means that it's not affected by the merger noise. You don't have here something which depends on sigma square of n. So it's a great advantage of this method because you get rid of the measurement noise. Yes, the same like the previous one, you can retrieve a positive value here, meaning it's possible that you have a covariance which is positive. But if you want to translate it into a variance, you will retrieve, in this case, a variance which is negative in the same problem because you have uncertainties. If you have a clock which is much better than the other one, perhaps it will, the small uncertainty on the variance will make difficult this difference. Okay, so you can retrieve positive value, and in this case, it's difficult. So I go back to the difference between the model and the measurement. What is my model parameter? The parameters are the Allen variance, which are obtained with the mathematical expectations, the Groslambert covariance, sorry, which have been obtained with the mathematical expectation, of course, which are not accessible. And what we measure are the covariance which are obtained with a finite average with m terms. And you see that there is a hat here to distinguish from the model parameter. And this is what I called theta in my previous talk. And here we have the Xi measurement, which are here. So as usual, we have to assess a confidence interval around the parameter theta A, theta B, and theta C, knowing the measurement Xi A, Xi B, and Xi C. It's always inverse problems that we have to solve. And we go from the conditional PDF of the measurement knowing the parameter, and you have to, it's a called direct problem, so generally it's easy to have an idea of what is this. Sometimes it's not so easy, but we will see that it's possible to get them anyway. And we will use the Bayes theorem by using the prior, which is here. So I will explain the principle of the KLTS method, which is a method which is used in sigma theta in order to retrieve the uncertainty of the covariance measurements. So we have, if we look at what are the statistics of the estimate sigma square A, sigma square B, and sigma square C, the measurement, what I call the measurements, we see that there are Bessel random variables, which is not exactly easy to handle because the Bessel random variables are a little bit tricky, and generally it's not tabulated in MATLAB, in Mathematica, and so on. So it was an idea of Eric Lantz to not work with this estimate, but to work directly with the measurements that we obtain from the time interval counter. Instead to use three G-cov, three Groslambert covariance, we use 3M random variables, which are the Z, because the advantage is that they are Gaussian. And if they are Gaussian, it's very easy to get their probability density function. So remember that there is a relationship if you add all the measurement coming from all the time interval counter, because you have here ZAB plus ZBC plus ZCA is quite easy to do for each value for each time value. And you can replace ZEB by ZB minus ZA plus ZM, the noise, and you can do the same for the other one. But you see that here you have minus ZA plus ZA, so you can remove it. You have plus ZB minus ZB, so you can remove it. You have plus ZC minus ZC, you can remove it, and you retrieve only the noise. So it's relatively easy to get the noise measurement directly from your measurement. You just have to sum all them. So it means also that the difference coefficient, the difference measurements ZAB, ZBC, and ZCA are not independent, because if you have no noise, for instance, the sum of these three quantities is equal to 0. So it means that there is a relationship between them. They are not independent. They are dependent. They are correlated. So we have to make them uncorrelated. How is it possible to make them uncorrelated? We can use the so-called Karhunen-Loeve Transform. The name is not important. What is very important, it's a quite simple system. You just have to diagonalize the covariance matrix. For instance, you can drill the covariance matrix of your data. But it's directly the variance of the given by the Allen variance of the result of time interval counter AB. The same for the other diagonal term for BC, the same for CA for the last diagonal term. And between them, you make directly the covariance between A and B here, between B and C, and so on. C and A, pardon, sorry. Yeah. You put the covariance here. So you can diagonalize it, or you can also diagonalize the parameter directly. You can retrieve sigma square AB by the parameter if you know them. Of course, generally we don't know them, but we will see that in our algorithm we will try to know them. Sigma A, sigma B, sigma M, which are the noise of the measurement and so on. So you can diagonalize this matrix. By doing that, you will retrieve, you rotate the covariance matrix, and you can rotate all the data, and you will pass from three parameters, which was sigma square A, sigma square B, sigma square C, to three new parameters, V1, V2, and V3. And we can get from your 3M, because there are three different counters, and M different time measurements, you will retrieve 3M uncorrelated Gaussian random variable that I will call W. Okay? It's just a rotation, a matrix of rotation. You have to figure out what is the space of the, one of the dimension is the number of measurements you did during time, and the other direction of the other dimension of your space is the three different counters. So, what are these new parameters V1, V2, or V3? They are nothing but the eigenvalues of the diagonalization. And what are the three M uncorrelated measurement W? They are it's a linear combination of the previous Z measurement with coefficients which are given by the eigenvector of the diagonalization of the matrix. So you are able to make this transform because you know the eigenvectors and you know the eigenvalues, of course. So the advantage, as I said previously, is the fact that the W measurements are Gaussian, uncorrelated now, and centered random variable. So it's very easy to know what is the PDF of these W measurements. So the calculation of the conditional PDF will be relatively easy because you know that you replace Z from W, and in this case, you can consider that the probability density function of the Z measurement knowing the parameter is given by this relationship, and you see that you are here a Gaussian, an exponential in which there is the W measurement, and you know that the probability density function of a set of measurements is the product of the probability function, but in this case, since it's an exponential, the product is a summation, of course. So you have the exact formula from the probability density function of the measurement, knowing the parameters. There is this is the first relationship, I will call it the relationship 1 here. There is another very strange idea which comes from Eric, but which is very clever. It comes from the so-called sufficient statistic property. Eric demonstrated that this sum, which can be a little bit long because sometimes we have many measurements, you can have several thousand measurements, several millions of measurements, because if you take one measurement per second during 10 days, you have approximately 1 million measurements. So if you can avoid to make this sort of summation, you can do. And you know that we already have computed the Allen variance and the covariance for all the data. So you can just use this relationship, the relationship 2, which will avoid to calculate all this, the summation which is here. It's much more direct. It's very simple. And in this case, you can compute the CDF, it means the cumulative density function integration by Monte Carlo random sampling. I will give you here really the heart of the algorithm. I will give you an overview, and you will see that it's not exactly what we expect, because it's another idea from Eric Lantz, because we choose to do that by using an integration by Monte Carlo random sampling. I explain what it means. You choose randomly a triplet of parameters, sigma A, sigma square A, sigma square B, sigma square B. And what is very important, you choose it in randomly, but with a random property, let's say a uniform probability in log. It means that you have the same probability to be between 0.1 and 1, to be between 1 and 10, to be between 10 and 100, and so on. So you take the log of the exponential of the classical probability. This ensures the fact that you will simulate a prior in 1 over theta. Okay, so in this case, you are sure that you will have no preference for any order of magnitude. So you don't choose, you draw randomly this set of 3 parameters. From this set of parameters, you compute the covariance matrix of the parameters directly of the parameters sigma square AB, BC, and CA from sigma A, sigma B, sigma C, and the J-cov. And it's relatively simple to do. It's only a matrix, which is a matrix 3 by 3. And you compute the eigenvector, the eigenvalues of this covariance matrix, so you diagonalize the covariance matrix, and you are ready to apply this rotation to the Z measurement in order to retrieve the W measurement. But it's useless, because we know that thanks to the property of sufficient statistic, you can use 1 and 2. So I go back to what I show you. You just introduce this quantity here, and you make this computation. So from this, you are able to compute the PDF for the one point. The point is the parameters that have been drawn: sigma A, sigma B, and sigma C. So you have 3 measurements of the 3 PDFs: the PDF for sigma A, the PDF for sigma B, and the PDF for sigma C. It's for one particular value. And you do that 10 million times. And it means that you will draw randomly 10 million parameters, set of parameters like that, and we will build what is the PDF progressively, but in disorder, because you draw it randomly, so you have to reorder that after that. After you have got your 10 million iterations. So first thing, once you got that, you make the sum of all that, and you know that you have something which should be normalized to 1. So you divide by the sum of all that. So you have now something which is like a PDF because its integral is equal to 1. You sort the parameters in ascending order because you remember that they have been drawn randomly, so they are in any order that has been sorted, so that have been obtained. So you sort them in ascending order, and after that you are able to compute the CDF, the cumulative density function, by making this cumulative sum. And the cumulative sum, it means you use the cumsum instruction of MATLAB, for instance, or for Octave, but this sort of instruction are generally available in any language. And once you get the CDF, you search for which argument of the CDF you will get 2.5%, for instance, or 97.5%. It will give you the bounds of your uncertainty domain. So the name is KLTS because it stands for Karhunen-Loeve Transform using Suffcient statistics. So, in order to illustrate what I said, at each random drawing that you have of the parameter, here you have the parameter, for instance, is the parameter sigma A. You have drawn, for instance, 10 to the minus 4, and it will give you a point which is here. You make another drawing, it will give you 10 to the minus 1. You see that it will be here, another one there, and so on. So you build progressively the whole PDF. And after that, you normalize in order that the sum is equal to 1, and you are able to make to compute the CDF, which is given here. The CDF is nothing but the cumulative sum of that. You see that if you have something which is constant here, you have a slope which increases progressively here, and you have integral of this is the integral of that. And what we obtain is directly the cumulative density function. So it means that here you are exactly at 0.025, and you have this value here, which is your bounds, and you find the bounds is 2.7, 10 to the minus 5. And the other bound is given here, and you have 97.5%, and you have a value which is 2.2. And you can also, if you want, if you are interested in, you can also obtain the median estimate, which is the one which gives you 0.5. And here it's 0.9. Okay, so it's the principle of the method. So in this case, we have an error bar on the parameter, which is between 2.7, 10 to the minus 5, and 2.2. There are arbitrary units, so it doesn't mean that we have make the computation. It's really an over-simulation, but it works with value, with standard Allen variance, and so on. You see that in this case, the interval is very, very large, of course. Second thing, it's very important to check if our method is good or not. And in order to check this method, we have built another algorithm, which is not an algorithm to compute the result, but an algorithm which will try to give what is exactly the inverse problem. So in this case, for instance, you select a set of 3 estimates. I mean measurements. It's very important. This is a target. And once you get that, you will draw randomly a set of parameters, and you will try to, you will compute the estimate, you will randomly draw 3n measurements corresponding to this parameter. So this is the so-called direct problem. So you will retrieve here 3n z coefficients, z measurements, which correspond to this set of parameters. You compute from them the Groslambert covariance and the variance, and you verify if it's equal, if the estimates are equal to the target. When I say equal, it's within 10%, for instance. The probability is relatively low. Generally, you have to draw another parameter triplets and so on and so on. But if yes, you know that the parameter triplets that you have randomly drawn are compatible with the estimate that you get. So they are able to furnish this sort of estimate. So you keep them. And you do that in order that you get 10,000 positive matching between the target and the estimate that you have here. And you have a set, once you did that, you have a set of 10,000 parameters which are able to give the measurement targets which are here. So it's possible that it's now something that you can use to verify the results that you get. Just in order to give an idea, for instance, here I have a target which is the measurement are for A 0.1, for B 1, for C 1. You have an equivalent degree of freedom of 5. All that has been determined. It's something that you can change if you want, of course. You can look at that if you vary the ADF, if you vary the variance of A as you want. And what are the parameters which are able to give you this set of measurements? And you see that here you have a space where you have the 3 parameters. It's a logarithmic scale, but you have A during this axis, B along this axis, and C along this axis. And you see, of course, that maximum of them are in this area. In this area, it means that you have C, which is equal to 1, 10 to the 0, B, which is equal to 1 also, B is here, yes, C is equal to 0, B is equal to 0 also, and you have A, the maximum is about, yes, I think -1, so it's 0.1. But you see also that there are many parameters A which are very, very slow, very, very low, sorry. You have some parameters which are 10 to the -3, but it means that it's very difficult to know from this what is exactly the parameter which can give you this parameter, because it has been drawn by the other parameters. You have also some very rare case in which you have a bad estimation of, it's not a bad estimation, but you can obtain this set of parameters, this set of measurements, sorry, from parameters which are quite different, because here you have, for instance, you have the parameter C, which is equal to 10 to the -4, for instance, and the parameter A, which is approximately equal to 1, and the parameter B also equal to 1. So it can happen. So now it's possible to make empirical confidence interval if I make some tests. So this graph shows you what were the possibility to make to compute uncertainties of three-corner hat. It has been done by the first one is a Gaussian approximation. You can consider that you have something which is Gaussian. It's relatively correct if you have a number of degrees of freedom which is relatively high, for instance 100 here, or more than 100. There is another method which was given by Ekstrom and Kopang, and there is a method that on which we worked before the KLTS method, which was a method with approximations, which was called KLTG, G for Gaussian. We have an approximation of Gaussian, which is not true, of course. And you see that neither of this method, the red one is the KLTG, the gray one, which is here and which goes here, just here, is the so-called Ekstrom Kopang, and the blue one, which is a Gaussian approximation. So you see that it's relatively far from the error bar, so it doesn't work, except if the number of degrees of freedom is greater than 100. What we obtain with KLTS, you see we have a perfect fit, perfect perhaps not, but a very good agreement between the error bar which have been obtained by searching for the statistic with the method that I have just shown you, and the method KLTS. KLTS is done very good result, even for very low EDF. This is an example with 3 estimates which are the same level. We have one for A, one for B, one for C, and we neglect the noise in this case, but we can do that by changing the noise, by changing the variance of one of the clock. For instance, here we change from 0.5 to 100 along this axis, and you see that you are still perfect agreement between the error bar, which have been computed independently, and the algorithm KLTS, which is here in colored area. Okay, and so this yields to the slide which present what has been done with true clocks, and it was something which has been published in 2018. I don't remember. We can confirm because many people in this room were in this paper. It's the comparison of 3 CSO femto, and you see that here you have the measurement noise, which is which decreases very quickly, and you have also the uncertainty, which are given by area, colored area, in pink here, in blue here, in green here, and you see what we can say about that. You see that, for instance, this one is the best clock, and when you have the clock, when you look at the best clock, the stability of the best clock is difficult to assess, because you try to assess the stability of a good clock with two other clocks which are not so good. So you have a very good assessment of the stability of this one, which is not so good, but it's difficult to get this one, particularly if you have a large value of tau, because it means that you have very small EDF, and you see that here it's not possible to know where is the bound at 2.5%. It's something which could be 10 to the minus 25 or something like that, but it doesn't make sense. The result of that is the fact that you are obliged to consider that what you know about this clock is the fact that its stability is at 95% below this limit. But you are not able to say what is the stability exactly of this clock. You see that if you use an estimate, for instance, this is the direct estimate of Zhikov, you obtain this value, but if you use a median estimate, you obtain something which is 10 times lower. So the estimate themselves doesn't carry any information with significance. What is very important in this case is the fact to be able to know that I don't know what is the stability of my clock, but I know that it is below. In this case, you have something which is about 3 10 to the minus 16 for this tau value. Okay. So to summarize this first part, I will say that KLTS provides a CDF of Zhikov. So the CDF provides confidence interval for the Groslambert covariance estimates. It provides, if you want, median estimates, but generally it's not so useful. KLTS is a rigorous method because there are no approximation, there are no simplifying assumptions, except when you say that you have some for instance, we consider that we have no correlation between the samples. And it's based on the property of Suffcient statistic, which decrease the number of computations that you have to do in order to get the result. It's valid for very low equivalent degrees of freedom, even 1. It means the most right-hand side the tau value if you build Allen variance. And it has been validated by massive Monte Carlo simulation, because I show you just 2 examples of the Monte Carlo simulation, but we did a lot of this sort of simulation by varying the number of degrees of freedom, by varying the variance of each noise and so on, and the measurement noise. The only drawback of this method that we have seen is the fact that it is possible to compute the CDF if you have high degrees of freedom. But it's not really a problem, because if you have a high number of degrees of freedom, it means that it can be approximated by Gaussian or by the other method which is used in sigma theta, which is KLTG, which is perfectly reliable above 100 ADF. So if you want to use this method, you have to use KLTS if you have very low numbers of degrees of freedom in the right-hand side part of the graph, and for the left-hand side part, we can use KLTG, for instance, and this is implemented in sigma theta. So if you use sigma theta, you will directly use this formalism. Okay. So I will switch now to the last part, but it will be a little bit shorter. Don't be afraid. About cross-spectra, I will just give you a brief overview of what we did, of what Antoine did with cross-spectra. So what's the problem? The problem is that you have a source, I will call it S, and you have two instruments, A and B, and you can process the result of the measurement and give an output. So what is the source first? The source may be two radio telescopes, because with Antoine we were also interested in observing millisecond pulsars, for instance. So you can imagine that you observe the same pulsar with two radio telescopes. But of course, it can be a measurement like the ones that Enrico did, which is a device under test, which is compared to a clock A by using the instrument A and a clock B by using the instrument B. And after that, you make a correlation at the end. So it's the cross-spectrum method. So assumption, as usual, you consider that S provides a stochastic signal XS, and its variance is sigma square S. So it's the variance of the signal, sigma square S. And the instrument A introduces a noise, which is XA of t, and its variance is sigma square A, the noise variance. And you have the same for the first, the output arm. The output of arm A is this one, XSA equal XS plus XA, and of course, it's the same for the arm B, and the output of arm B is XS plus XB. Okay. We consider that all noises are statistically independent, as usual, and we will consider also that the noise level of each arm is approximately of the same level. You have the same variance, the same noise level in A and in B, but the noise are uncorrelated. The noise of A and the noise of B are completely uncorrelated. Generally, we consider that it's white noise. So in this case, we can consider that in each case, sigma square SA and sigma square SB is equal to the sum of the variance of the signal plus the variance of the noise. How is it possible to estimate sigma square S, the noise, the level of the signal? And incidentally, if we can estimate this, you should be able also to estimate the variance of the noise level. So, first of all, we have to go back to the principle of the correlation radiometer, which has been invented by Hanbury Brown for radio astronomy in 1952. Thank you, Enrico, for this reference, which is a very basic reference of this. So we have two instruments. You have an output, which is a correlator, in fact, and you will make a correlation between arm A and arm B. So if you develop all that, you will see that there are many cross terms. And since each noise are uncorrelated with the other ones, it means that every correlation will tend towards zero, except this one, the signal one, because XS correlated with XB will be equal to zero in average, XA with XS will be zero in average, XA and XB, of course, will be zero in average. So all this cross term will be equal to zero in average, and you retrieve the autocorrelation of the signal, which is XS here. So the instrument noise vanished. This is really the interest in average. It's really the interest of the cross-spectrum method. So we have to be sure also of what we will deal with. If you have X of t, which is a noise like that, this is the signal. We have X of t. If you do the Fourier transform of that, this is random. This is random, but you see that there is a long-term behavior. It's perhaps 1 over f, perhaps a mix of 1 over f and 1 over f square. And if you take the Fourier transform, we will retrieve a random noise here, but you will see that the amplitude will be larger at the beginning because it's 1 over f, and it will decrease when the frequency increases. Okay. So we can do directly, if you have 1 second, we can directly compute the periodogram. The periodogram is nothing but the square of the modulus of the Fourier transform. So from this dots which are here, you take the square of the real part, which is in blue, plus the imaginary part, which is in orange here, and you will get this curve and log, and this is the so-called periodogram of the signal. But what we are interested in generally, it's the polar spectral density. The polar spectral density is something which is not random, which is smooth. It's a green curve which is here. And the spectral density, of course, is as usual a mathematical expectation. It is in the model domain. And you have to imagine that you make several periodograms. For instance, you can several periodograms. If one measurement of a periodogram lasts 1 hour, you will do another one the next hour, another one, and so on, and you can retrieve, let's say, 100 periodogram like that. You make an average of all that. Theoretically, it should be an infinite average, of course. But you can also imagine that you have exactly the same the same experiment, which is duplicated n times. It's a little bit strange, but it's an ensemble average in this case, and you can consider that for 1 time you make the average of all what happens with this equivalent experiment. So what is interesting in this case is the fact that we will have a PSD estimator, which will be something between the periodogram and the PSD, because the PSD, of course, is not accessible, and you will use the periodogram, but you will use a finite average of periodograms. M is the number of periodograms that we will use. We will make an average over M different periodograms. Okay, so we are searching for what happens to, for instance, this frequency. You can, after that, of course, change of frequency, but we will look at what frequency bin, and all the developments that I will show you are given for 1 frequency. Okay, you can imagine that we'll change the frequency after that. So we are focusing on the frequency F0 here. But what are you searching for? Are you interested in the periodogram, or are we interested in the polar spectral density? Strangely, it depends of what is your problem. If you have a problem, for instance, in astrophysics, if you are looking to millisecond pulsars, sometimes you are observing a frequency which is 1 over 1 year, for instance. So it's not possible to make several measurements with different times, because you have to wait at least 1 year for give 1 point, to give another year to give another point, so it's a little bit longer. So in this case, what we can do is to observe at the same time the same millisecond pulsar with several radio telescopes, and to use this cross spectrum at this time. So in this case, you can increase the number of spectrum, but in this case, what you are looking for is the periodogram, because you are looking at what happened at this particular random sequence at the same time. So it's a periodogram. But generally, when we deal with oscillators, you try to obtain the polar spectral density. And in my example, we will try to obtain the polar spectral density. This question of between periodogram or spectral density is obviously not relevant if you use only 1 system, because in this case there is no average. In this case, it's a chi-square distribution with 2 degrees of freedom. That's it. So we have our 2 arms which are there. We consider that XA and XB are uncorrelated, the 2 noises introduced by the measurement device. And you can consider also that sigma square n is equal to the noise, the variance of the noise is the same for A and B, so it's a noise level. And we'll consider that the signal, XS, is a normal complex random variable. More or less, it's generally red noise, but it could be different. by opposition to the measurement noise, which is generally white noise, but we will not use the fact that it's noise, that it's red or white anyway. So what is important is the signal level, sigma square of S. This is really what we are searching for. So in order to be fair, we will look at too many approaches. The first one is a cross-spectrum approach, which has been described in this paper of 2010. And it has been demonstrated by Enrico that, in fact, when you want to get an estimate of the cross-spectrum, you don't need of the imaginary part because all the information is given by the real part. So you just have to multiply what is given by the arm A, XSA, multiplied by the complex conjugate of what is given by the instrument, the arm B, XSB. And so if you make the mathematical expectation of this estimate, you will retrieve, yes, if it's the mathematical expectation, you will retrieve the parameter. And this parameter is unbiased because you see that if you make a mathematical expectation of this quantity, you retrieve the signal level. You can compare that to a spectrum average, which will do only the average of these two quantities. So you take the real part of that, you divide by 2, take the square, and you do that also with the imaginary part. Of course, if you make the mathematical expectation of this quantity, you will retrieve the noise signal, the signal level, here, but also the noise level, which is here divided by 2. So it means that it's biased. But it's very important to consider this quantity. I will explain you what is the importance just later on. But it's relatively easy to unbiased this estimator because you just have to subtract here by the variance of the noise, by half the variance of the noise. But you need to know what is the noise level. If you know the noise level, you can have an unbiased estimate, which is here. Okay. Remember that the relevant parameter theta is sigma square n over 2. It's 2 because we have only 2 degrees of freedom. Because it's a real plus imaginary part. But it can be 2m if you have m, an average of m value. So this is a relevant parameter because it means that you can determine what is the signal level, but you have a problem with the noise. If the signal level is very low regarding the noise, it will not be possible to distinguish, and the result will not give you the signal level. Okay, so it's quite easy to know what is the probability density function of the measurement knowing the parameter, because it's given by this relationship. You see that sometimes you have negative results, so the negative results are given here, and sometimes you have positive results. It depends on the signal-to-noise ratio. What is important to see in this formula, you see that it's only a decreasing exponential in each case, but the decreasing exponential is divided by the variance of the noise here. It is divided by the variance of the noise plus 2 times the variance of the signal here. It means that in this part, you have an information about the variance of the signal. But in this part, when you get a negative estimate, you don't have any information about the noise, the signal level given by this function. It's not in this equation. So it means that you can put to the garbage of the negative estimate. No, it's not a good idea. What I mean is there are no information about sigma square S, by the signal level in negative estimate. So it's a so-called variance gamma distribution. So it's called the V-gamma method by Antoine. Of course, you see that in every case, even if you are with if you want to know what is the PDF, the probability density function, even if you use the method, the cross-spectrum method, you need the knowledge of the noise level. So what is the method? It's, as usual, a Bayesian inference. We have the PDF. I show you the PDF of the estimate knowing the parameter, but we have to know the inverse, the PDF of the parameter knowing the estimates. So we will do the inverse problem. You will make, as usual, the Bayesian inference, which is here, and you will have to determine the prior. And this time the prior is a little bit different because, as I told you, what is the relevant parameter is not 1 over the signal noise, the signal level, sorry. It's sigma square n over 2 plus sigma square s. So it means that in this case, you have the 1 over theta prior will give you the classical 1 over theta, which is here, but we are, our basic variable is not theta, it's sigma square s. So if you express this formula in case of sigma square s, you have this prior. So it's quite different. And you have here a prior which is given by this relationship. So you just have to multiply the previous equation which gives the PDF of the measurement knowing the parameter by this prior. And you do that, you make that, and you obtain, if the estimate is negative, you obtain this value. If the estimate is positive, you get this formula. And you see that it's perfectly in perfect agreement with the empirical post-PDF that we did, because we had also a method to find the empirical post-PDF. So we have here the advantage that an analytic solution exists. So it's quite simple to know that. And after that, you have to make the CDF. So you have to integrate this formula. It's possible to do that by integration by using Mathematica, for instance, and to retrieve, for which case you have 2.5% or 97%, 97.5%, and so on. So it's possible with this method to get the probability density function of the signal level estimate sigma square s when using the cross-spectrum method without approximation. If you have only one cross-spectrum, m equal 1, you have exact analytical PDF of the variance estimate, so it's very simple. It gives you directly the result. But we see that generally it's only possible to have the high bound, the high level, because the low level is very far and it's not informative. It's the same that I explained to you with the three-corner hat. It's relevant for one or several measurements for m greater than 1, and if you have m which is greater or equal to 1, it allows the determination of confidence intervals through numerical integration, and m superior to 1, greater than 1, but greater or equal, it's a mistake. So the noise level of each measurement instrument has to be known in any case, even if you have if you use the cross-spectrum method. So I think this ends my talk, and I thank you for your attention during this talk. I hope you have questions. I think I'm not. If someone is a precursor in this job, is Enrico. But I think it has been. It's very used also in astrophysics, for instance, because people using a radio telescope in order to observe the signal from a millisecond pulsar are using massively cross-spectrum and so on. And the goal was very important, because before 2015 there was a challenge between astrophysicists and physicists in order to observe for the first time the gravitational waves, and people observing the millisecond pulsar try to observe directly the signature of a gravitational wave, but it's too late now. It has been the job has been won by LIGO and Virgo and so on. But it's something which is very used, of course, in many other disciplines.
The conclusion is that you need the noise of the instrument in all cases. Yes.
If you want to get an uncertainty domain, you need to know the you can use the estimate directly without knowing what is. But if you want to get an error bar, you need to have an idea of what is.
The thing is that if you know the noise of the instrument, you access to the total power radiometer, which is the dream of radio astronomers.
Yes, but when I say to know the noise of the instrument, I mean to have an idea of the noise of the instrument. You don't need to have a very precise idea. What you need is to have an order of magnitude in order to give you an uncertainty
broad
domain.
Knowledge, not the value.
Yes.
All right.
An uncertainty domain is something which is always given with two significant digits maximum, but generally it's one significant digit. You just have a domain, and you don't try to have a very precise value with 3, 4, 5 digits after the dot.
One more comment, there are many discussions around this, because in the cross-spectrum you need 2 instruments. And with the 2 instruments, you can play the trick of the Dike radiometer, swapping the instruments. One measures its own noise, and the other one measures the signal.
Yes, it has been studied by with Antoine, because it checked really what is the best between the Dike radiometer and the approach of the cross-spectrum. And if you know perfectly what is the noise of the instrument, it's just a little bit better to use the Dike approach than to use the cross-spectrum. But of course, generally it's not possible to have a perfect knowledge of the noise level. You just have an idea of the noise level. So in any case, it means that the cross-spectrum is better. And if you increase the number of the average, if you have an average of 10 or 100 cross-spectrum in order to get the result, it's definitely better.
And there's another dimension in this discussion. In some cases, you use 2 radio telescopes, so one telescope does not take away the signal from the first one.
Sorry?
When you use 2 radio telescopes,
yep,
you just add the signal, the total signal you have access. If in electrical measurements, instead, you split the signal, so you lose half of it.
Yes.
And this is a different.
Of course, that's right.